All right, so in this lecture, we're going to go through volcanoes. So we've learned a little bit about igneous rocks in general, and then we're going to get just a little more focused on volcanoes. So still, we're going to talk about rocks because volcanoes are the extrusive equivalent of some of the intrusive rocks we looked at. And so these are all materials that have made it to the surface and cooled on the surface. But in particular, we want to look at different types of volcanoes, how they erupt, and some of the hazards that are associated with them. So for this lecture slash PowerPoint, I'm just going to walk through the different types, and then we want to relate it back to their compositions, because this is one of the things that's dictating the type of volcanoes that we're going to see. And so remember the terms mafic, felsic, and intermediate. Those are composition terms that we learned, and they play a role in how volcanoes erupt. So let's see what we got here. We are going to move through. And so one of the things, of course, that we can talk about is eruptions and what has happened here in the U.S. in 1980. We had a volcano that erupted called Mount St Helens. It started out looking like this, a typical, what we're going to come to find out is called a stratovolcano or a composite volcano. You can go ski on some of these mountains. There's one like this in Flagstaff if you're here in Arizona. But of course, after the eruption, it looked a little different. And so certainly this was a fairly violent eruption. Lost a lot of material from the top of the volcano, was ejected out into the atmosphere. Some of it was a blast. And then that material was deposited on the surface. Now, certainly we can eject some material high into the sky, and then it would fall down as ash. But then those little particles are hot enough that they can actually be welded together and form a volcanic rock. Of course, lava can flow out from these eruptions, and even particles, what we call pyroclastic flow, which is kind of these pieces and particles that are ejected from this pressure, pushing these pieces outward across the landscape. And then those, of course, can cool and then weld together and form a different type of igneous rock. So why do we get these big violent eruptions? Well, there's a couple reasons that this occurs, but one of the big drivers is there's a water in the magma. And so this probably sounds a little counterintuitive because we're thinking it's extremely hot. And so how do you get water in the magma? So of course, it's not like buckets of water. We're talking, molecular water and things like that. But remember, under the pressure, we change some of the conditions with which materials change phases. And so water can change from a liquid to a gas under certain temperatures. But when we have a high pressure, we elevate that. So, here on the surface, we can take water and turn it into steam at, let's say, 100 degrees Celsius or 212 Fahrenheit. But when we put pressure on that material, then we can change that to a higher temperature. So in the subsurface, when we have a lot of pressure, the weight of the overlying rock on the magma chamber, we have water that's still water. And of course, we have some other gases that are dissolved within the magma. When we release that pressure, this is where we can get the power to push the material upward and outward in a violent manner. So the more gases and water that we have in the magma, the potential to have a violent eruption is there. But it's not the whole story, of course, because the other thing that we want to talk about is composition. So this is why it was important to talk about, the mafic, felsic, intermediate story. And the thing that we want to focus on for this class is the CO2 content, right? So we said that the silicate minerals, which make up our igneous rocks, have a variety of percentages of silica in them. And we went from the mafic to the intermediate to the felsic, and the mafic had the least amount. So a low silica content for mafic composition magmas and lavas. They tend to be these dark ones, right? So high iron and magnesium make it dark because there's a lot of dark minerals. But what that does is it allows it to flow a little easier. And so we're going to introduce this term viscosity, which is resistance to flow. And so what happens with a low silica content is there's a low viscosity. So a low resistance, which means there's not much resistance. These type of magmas and lavas can move fairly easily. They flow. So if you want to think about mafic lavas, we want to think about like the Hawaiian Islands. And so those are the things that flow along the surface. At times they can move fairly quickly if they're close to the source and very hot. But what happens here is even if there is some dissolved gases in there and water, because it's very fluid, it allows some of the gases and stuff to escape fairly easily, tends not to be very violent. So this combination of a low viscosity, which we're arguing is related to the compositions of the magmas and lavas. If they are mafic, they have a low silica content. This means that they flow easily and things can escape easier, and so they don't build up pressure. On the other extreme, where we have felsic lavas, so this is the high silica content magmas, they have gases and water dissolved in the magma, but because they're so sticky and they do not flow very well, the gases have a hard time escaping from there. And so what happens is pressure builds because the gases keep growing and growing. And especially if we release the pressure, then the gases expand, the water turns to steam and expands. But because it can't get out, that pressure grows until it exceeds the strength of the rock around it, and we get a violent eruption. So we're going to say that felsic magmas are the thickest, right? Because they have a high silica content, a high viscosity, which means a high resistance. They don't want to move. And we combine that with any dissolved gases or things that are changing from one phase to another and expanding. That is the driver there, and we can't get that out. Boom, we get a very violent eruption. And so there's everything in between, of course, from the mafic that are super fluid and not very explosive to the highly viscous, viscosity, right? High viscosity, felsic magmas that are very thick and gooey. And if there's enough gas in there, then that can be the combination for a very violent eruption. So remember, where do we have these? This is just kind of reminding you of some of the compositions, right? These are the terms we've been talking about. And we've been talking about the silica content's important, especially when it comes to volcanoes. So low in mafic, so a low viscosity, high in felsic, high viscosity. We find felsic rocks in the continental crust. We find mafic rocks in the oceanic crust. And remember, the mantle is ultramafic. But when we talked about igneous rocks, remember, we said that we can combine these things, right? So when we partially melt the mantle, we initially get mafic magmas. But as they move up through the crust and lithosphere, if they're over here in the ocean, we have a mafic melt that might be at a divergent plate boundary or something. As that moves up and interacts with other mafic stuff, there isn't a huge change in composition. So we wouldn't expect a very violent volcano or eruption to occur there. But here in the continental crust, I have felsic material. And I can add that to my mafic magma that I get from subduction. It moves up into here. At times it mixes. So I have mafic and felsic mixing, and I get an intermediate. It has enough silica that it can trap gases and it can lead to some violent explosions. The more felsic it is, potentially the higher the explosivity is. And the more mafic it is, the less. And of course, then we have hot spots too. We've mentioned Yellowstone is a hot spot that's coming up into the continental crust, and it has the ability to create very felsic magmas, and these can lead to very violent eruptions. And so we see, relating everything else we've talked about, plate tectonics. Remember, this is where we're generating our magmas, from subduction to divergent plate boundaries to even hot spots. But, if we look at here where we have subduction, we get lots of volcanoes here, but here. And so this story of the Ring of Fire is kind of this area here that surrounds the Pacific Ocean. And of course, it's called that because we have subduction here generating magmas, which then, of course, generates volcanoes. And there's the term, fire from all the explosive eruptions that we get here. Okay, so let's talk about the different types of volcanoes that we can get. So we want to run through a handful here. And we're going to relate them to their explosivity, and we're going to relate it to the composition. So here we have what are called shield volcanoes. So these are very broad and flat types of volcanoes. So they're not the typical volcanoes that you may think of when you envision a volcano, right? A kind of a sharper peak, something you might go ski on, like the Cascades if you've been up into the Pacific Northwest there. So these are very mafic, and what dictates their shape is their composition. Because they flow very easily, they flow for long distances. They don't build these really steep-sided volcanoes. They build these huge, broad, flat volcanoes. And so the Hawaiian Islands is a great example of that. Now, they seem kind of tall and jagged because, of course, there's been erosion, lots of other factors that are dictating its shape. But if we take a step back and look at its overall shape, we would argue that it's kind of broad and flat. And so that's the composition is dictating its shape, and it's also dictating its explosivity. And so because we have this very fluid magma that's low in silica, it allows gases to escape. So there isn't a lot of gas in there because it can escape easily. So there's not a lot of buildup of pressure, and so we don't get these very violent eruptions. Now, doesn't mean we can't, I'm sure you've seen some images where you have a fountaining of lava. It gets like thrown up into the air, but maybe hundreds of feet, not this, thousands of feet or kilometers into the air if it was more explosive. And so a hazard here isn't a big explosion. A hazard here is the flows going along distances, interacting with structures or people or things like that. Those are the things we have to be concerned with shield volcano type eruptions. And where do we get those? Of course, we can get those in the place we've been referring to, which is Hawaii at hotspots. Because our hotspot is under the ocean, it's oceanic crust that is being intruded into by our mafic magma that's at depth. And as it comes up and it interacts with that material, we have mafic and more mafic. There's not a way to really change the composition of the magma. We end up with a very mafic eruption. And of course, because of its composition, this is kind of what we get. And here's some examples of that. And even in Arizona, there's a small little shield volcano called Joe's Hill. If you've actually been up I-17, it stopped at Sunset Rest Area. If you look to the east, that's where Joe's Hill is. There's a very thick deposit of basaltic flows that have flowed out in that area. Of course, their basalt means that they're high in iron and magnesium, low in silica. They flow for long distances, so you just get this broad, flat kind of feature here that you wouldn't maybe think as a volcano, but if we look at the compositions, we can see that it is a volcano. Now, as we move down our kind of composition story, so remember, we're going to argue that mafic, low in silica, and then we go intermediate, it's kind of in the middle, and then we go to felsic, really high. And so here we're going to say that we are moving down a little bit. So we're still kind of in the mafic story. We get these volcanoes called cinder cones or scoria cones. They are still in the kind of mafic area, but they're moving down the ladder just a little bit. What makes these a little different is there's a little more gas that's trapped in here. Now, not enough to make a huge, blast that devastates, hundreds of square miles, but enough to throw material into the atmosphere a little higher. And so what we do is we get these little fragments or pieces called cinders or scoria. They're still dark because they're mafic, iron, magnesium, but they get thrown up into the atmosphere here, and then they fall back down and they build a cone. Now, these typically aren't huge. They're not very big volcanoes relative to certainly shield volcanoes and even our more common stratovolcanoes, but they show up in lots of places. And so we can get these in lots of different environments. Even where we have lots of intermediate volcanoes, we get these. Even where we have felsic volcanoes, we can get these. Mafic volcanoes, we can get these. And so they kind of show up in lots of different places. And, they're a little more explosive than our shield volcanoes, but not extremely so. And like I said, their size kind of dictates, what they are. And great examples, of course, even in Arizona, if you go up to Flagstaff and then head kind of to the northeast, you can kind of see Sunset Crater or SP Crater. These are cinder cones. And if you've walked in this area, there's lava flows like we would expect because it's sometimes very fluid, but in times where there's a little more gas trapped, we get these eruptions that deposit these cinders. So basically it shoots up into the atmosphere and then falls back down and builds a cone. And there's lots of little cones in Flagstaff, so if you're ever up that way, you can kind of cruise through there and see those types of volcanoes. Now, this is the most common type that you see, and this is probably what you think of when you think of volcanoes. They're called stratovolcanoes, sometimes called composite volcanoes. This is kind of the intermediate composition. So we've moved down our ladder, we've increased the silica content, we've increased the trapped gases and liquids content. So that combination can lead to violent eruptions. Now, sometimes we can get a less violent eruption, and one of the reasons it's called a composite is because it's made up of kind of different types of eruptive styles. At times we can get a lava flow. It oozes out the top, flows down the sides, but it's not super fluid. It's not like a mafic shield volcano that runs for hundreds of miles. This is thicker. It can't flow that far, and so it forms steeper, broader kind of shapes. And then the second type is where we have a more explosive eruption that ejects material into the atmosphere that falls down and coats the sides and builds up our volcano that way. So it's a composite of lava flows and what we're calling pyroclastic layers, right? Pyroclastic pieces, fire. These are pieces that are ejected and fall back down. And so we get this type of volcano called a strato or composite. So we can kind of go through the properties, right? It's more eruptive or more violent, and that's because of its composition and its potential to have more trapped gases and fluids in there. Mount St. Helens is an example of this. Typically, if we want to say where do we get these, it is at convergent plate boundaries, specifically or especially where we have an ocean plate running into a continental plate. And why is that? Remember, that's where we get initially a mafic melt. It rises up, it hits the continental crust, which is felsic. So now I have mafic and felsic material that I can mix together, and I can get something in the middle. Now, does that mean that at that boundary we only get intermediate? Well, it doesn't, but it means that the vast volume of material that's being produced there is intermediate. Can we get more felsic stuff? Sure. Can we get more mafic stuff? Sure. But in general, the volcanoes and features that we see at convergent plate boundaries is going to be intermediate. And that's what we see in that whole ring of fire. Most of those interactions at those boundaries are ocean hitting a continent, and so we get lots of intermediate. Now, are these the most violent ones that we see? They're not the most violent because they are not kind of the thickest magmas and lavas, and they don't trap the most gas. But these are so common, way more common than other volcanoes, that they still pose the greatest hazard because they're everywhere when we talk about these types of volcanoes, and they have the potential to be very violent. And so if we look at the Pacific Northwest here, we have a subduction zone here. We're getting these volcanoes. Mount St. Helens erupted here. Lots of other, Mount Rainier is here, Mount Jefferson. These are all composite volcanoes with the potential to erupt violently and also to not erupt super violently, right? So we can have a variety of eruptive styles here. And of course, we have different hazards. So our shield volcanoes, flow hazards are big. Here, these explosive eruptions are a problem. And also other types of hazards, like we'll introduce a term called a lahar. What's a lahar? A lahar is a mud flow, but it is a volcanic generated mud flow. So imagine, Mount Rainier has a lot of snow on the peak. And so if there's an eruption, even if it's not a blast eruption, let's say there's a lava flow that flows out at the peak and starts flowing down, it melts all that snow, turns into water, and now I basically have a big rush of water moving down the sides of the volcano. And so a big mud flow that can race down the sides and travel for long distances. So even though I didn't have a huge blast, I still had a hazard, and it was associated with this type of volcano. If we look at some examples, Arizona once again has the peaks. If you go up to Flagstaff, you can see the remnants of a composite volcano that erupted here, 1,750,000 years ago. And so it also blew a lot of the material out, like Mount St Helens, and we're seeing the remnants of that. So if we look at our three we've kind of talked about to give you an idea of size comparison, remember the cinder cones are these smaller profile volcanoes. They're not super violent, but they can show up in lots of different places. Here's our composite. Of course, this is where the collision between the plates and there's subduction going on. We get this intermediate. And here's the felsic version. And you can see, if we put Mount Rainier next to this, Hawaiian one, holy cow, the difference is very extreme. So that may be helpful to give you kind of a size difference there. That's just a little imagery to show us where we're getting magmas and kind of how we get volcanoes, right? Moving along, we're going to introduce just a couple more volcanoes. Now, we get this thing called a lava dome. So lava domes I'm going to classify almost like a cinder cone, in that it can show up in a couple different places, and they're fairly small. They're not these really big features. But they are, as we move down the composition scale, very felsic. And so what we see is this felsic material that potentially could be violent, but it tends to not have a lot of water and gas in it. And so although it has the potential to trap a lot, there doesn't seem to be a lot, because a lot of times it's a secondary feature. And the images you're seeing here on the slide is a small lava dome. That's this thing. This is a lava dome, It's coming into a composite volcano. So the idea is that after every eruption, we can kind of change the composition of the magma chamber, because as we eject some material, we leave some behind. It has a little different composition. So then we get a secondary feature that develops called a lava dome. But it is very felsic, but typically it is not super eruptive, a very violent blast, though it has the potential to be unstable and kind of collapse and produce some of these flows, these pyroclastic flows. But that's kind of the lava dome, a smaller feature. The last one we'll talk about volcano-wise is what's called a caldera. Now, there is some confusion with calderas, the term caldera. A caldera is a collapse feature related to an eruption. And so this image here kind of shows it fairly well. We have a magma chamber at depth. We get an eruption. A lot of material is emptied out of this chamber, so there's some empty space here, and you can get a collapse of the overlying rock into that empty space. So you can get a caldera feature in some volcanoes, but here I'm going to use the term to refer to a caldera volcano. And so this is specifically kind of being used to describe Yellowstone. Yellowstone is an enormous feature. It's a caldera volcano. It has collapsed so much that you basically can't even tell there used to be a volcano here, because it's such a large feature. Here, we're going to say that this type of caldera volcano is very felsic, and it has a lot of trapped gases and liquids, which can result in an extremely violent eruption. So if you've watched some Discovery Channel stuff about Yellowstone, there's some stories that it will erupt someday and potentially do some devastation to the world. It has the potential to impact us for sure, and it would be much more violent than anything we've ever seen. So we can look at deposits to kind of think about what its potential might be, about the amount of material that it can deposit and eject. And so they are very violent. Why? Because of their composition and the trapped gas there. And so certainly, Yellowstone is a good example of that. Also, once again, Arizona, the superstitions are a collapse feature relative to a large eruption. And so the material that you see there when you go driving through the superstitions or go up to Canyon Lake, that is very felsic material. If you've hiked in that area, a lot of the rocks, at least on a fresh surface, are light in color, telling you that they have a lot of silica content, and that makes them very felsic. And so this is the remnants. If you looked out that way and said, oh, it doesn't look like a volcano because it doesn't have steep sides, that's because it blew its top and it exploded and deposited stuff. Of course, it's been weathered and all those other things. But the Superstitions is an example of a caldera type volcano. And so those are the main, let's see, what we do? 5? We had the, shield volcano. We had cinder cones. We then had the stratovolcanoes. Those are the most common and the ones we usually talk about the most because they're in a lot of different places and they have a variety of hazards. We do have the lava dome, that small feature, and then the caldera type volcanoes. So those are the different types and these are the properties associated with them. And then we'll talk just really briefly because we're talking about volcanic, features. You remember at mid-ocean ridges, we tend to get volcanic activity. Not always do we get a steep-sided volcano that's here, but we know that it should be basaltic, very mafic. Why? Because, of course, we have a mafic melt initially. It's interacting with a mafic crust, and so there's not a lot to change its composition. We tend to get these, magmas coming to the surface and then cooling under the ocean. And a lot of times we get these kind of bubbly features called pillow lavas, but the composition is what we would expect there. And because of its low viscosity, which means it has a low resistance, flows easily, not a lot of gases, and so not super violent. And so this is from some type of decompression melting that we get. And of course, it's because we're pulling the crust apart at a boundary here. And then all this is basalt. And so it's all mafic composition. This is why our ocean basins are mafic in composition, because there's no ingredients to alter its composition as it comes up and creates this new material here. So divergent plate boundaries is where we expect to see those, of course. And then we also have something called flood basalts. So there's examples in the Pacific Northwest of these very thick deposits of very fluid lava flows. And this is very mafic. You can tell by the color, they're dark. That's our suggestion that it is high in iron and magnesium, low in silica. And so because it's that composition, it flows for long distances, which it did. And if we look at the deposits, they cover large areas. It's kind of what they look like. They look like something maybe flowing out of like a Hawaiian island situation, except here, instead of being kind of a little point, it's actually in a fissure, a long, linear feature where there's a fracture, and this magma can come up and flow across the surface instead of just kind of a localized area where it can build kind of a shield volcano. This is a bunch of fractures that are, coming up through the crust, and we're getting this very mafic material flowing out onto the surface. And so it comes up and it just kind of follows these cracks and features. And here's an example of the extent. So this isn't, from a subduction zone here. This is from another issue that happened, before the subduction, and we had another heat source here. And of course, the crust was fractured enough that I could allow this material to come up and float to the surface. And so you can see the thick extent in some of these images here. Okay, Wrapping it up finally. So look, here's what we want to remember about the story that I just told you, is we want to look at the volcano type, or what we're calling the volcano. We're going to relate its explosivity and its shape to its content, its silica content, or its composition. And so we're calling this, the composition mafic, intermediate, or felsic. And so if it's mafic, has low silica. If it's felsic, has high silica. That dictates its viscosity. So low silica, low viscosity. High silica, high viscosity. Low means it can flow. And so any trapped gases or fluids can escape relatively easily, and we don't get very explosive eruptions. And we're calling those shield volcanoes, and places we can get those are hot spots and divergent plate boundaries. Stratovolcanoes are the next big type of volcano. Those are the very common ones. Those are subduction zones where we have collisions between plates because we're creating magma there. And then we have the potential to alter the mafic magma that's initially created. As it moves up through the surface, it can then be interacted with other materials, changing its composition. Here we're arguing it's fairly intermediate, so it can do a little bit of everything. It can have less violent eruptions, but it can have pretty violent eruptions. And because they're so common, these are the ones that probably impact us the most. And then we have calderas here, where our very felsic material, high in silica, high viscosity, lots of trapped gas. We get huge types of explosive eruptions. These, potentially impacting the entire planet type of eruptions. And of course, we did throw in the domes, don't forget about that, but it's a smaller feature that, is not very eruptive, violently anyway, because of its gas content. But where we see these big caldera type eruptions are these continental hotspots where there's a lot of felsic material available to us. And so that's kind of, we're going to classify those. So you want to just remember how the composition impacts the type that we get, and how it affects the viscosity. And then, of course, the gas content and water content combined. Those two things are going to dictate the type of eruptive style and really the shape. And so we want to keep that in mind when we're looking at volcanoes. And then, of course, we can use our igneous rock chart. So when we're doing lab stuff, and even when we're trying to identify different types of volcanoes, the stuff from fine grain down, this is the volcanic stuff. And so, if we wanted to put names to stuff, we would say, oh, the intermediate volcanoes should have a lot of andesite. That's true. The mafic volcanoes should have a lot of basalt. That's true. The felsic one should have a lot of rhyolite. That is true. Okay. And so these are the base rocks, the more common rocks. But when we have some explosive material and you get a lot of gas, you can get these types of rocks that are still fine grained because they made it to the surface, but they have additional features like holes, or they're super glassy, suggesting they cooled super quickly. And then we do have this pyroclastic version, which is the stuff that's ejected out from a more violent eruption. And so we can use that to kind of figure out what type of rocks we have. And of course, conversely, we can go back and say that those rocks relate to a certain type of volcano. Okay, so that was a long one and a lot of information for sure, but hopefully it makes sense that we're tying the volcano story back to composition story, which you already know, and also we're tying it back to plate tectonic story, which in theory you already know. So hopefully we can add those things together and you can see how these things kind of make sense, why we get volcanoes where we do, and in theory, what types of volcanoes we get because of composition, plate tectonics, and all that kind of stuff kind of merged together. All right. If you have questions about what I went through here and you'd like to email me, please do that. Otherwise, have fun, and you can use this information, of course, to help you with the quiz.